Welcome back. In this video, we're going to look at example problems of determining concavity for parametric curves. Let's get to it. All right, so here's our first example. We want to find the second derivative, d squared y divided by dx squared, and determine the concavity at t equals 2 for the parametric equations. And in this case, we have x equals t cubed and y equals t squared plus 5t plus 7. All right, so in this problem, we want to determine the concavity at a specific value of t for a curve represented by parametric equations. Now, whenever you're working with concavity or you want to determine the concavity of a curve, you know you're going to be working with the second derivative. All right, so even if this problem didn't say find the second derivative and determine the concavity, if you were just asked to find the concavity at a specific value of t, you know that you're going to need to find the second derivative. Because what we're going to do is find the second derivative for these parametric equations and then plug that value of t into that second derivative to see if that second derivative is positive or if it's negative. If the second derivative is positive, we know that the curve is concave up at that value of t. But if the second derivative is negative, then we know that the curve is concave down at this value of t. All right, and so in order to find the second derivative, we need to know the following formula, that the second derivative for a set of parametric equations is equal to the derivative with respect to t of dy dx, that's the first derivative of our parametric equations, divided by dx dt. All right, so before we can find the second derivative, we need to find that first derivative, dy dx. So let's find that first. And in case you don't remember, this is the formula for the first derivative. Dy dx is equal to dy dt divided by dx dt, the derivative of our parametric equation for y with respect to t, divided by dx dt, the derivative of our parametric equation for x with respect to t. And so let's find dy dx by first taking the derivative of x and y with respect to t. And let's start with x. Dx dt will be equal to the derivative of t cubed, and we will use the power rule for derivatives here. We'll multiply that exponent down and subtract 1 from the exponent. So we'll have 3t squared. And then let's find the derivative of y with respect to t. That's dy dt. That will be equal to the derivative of t squared plus 5t plus 7. Now using the power rule for derivatives, the derivative of t squared will be 2t, right? We multiply that exponent down, subtract 1 from the exponent, so we'll have 2 times t to the first power. All right, then the derivative of 5t, that's just going to be 5, so we'll have plus 5, right? The derivative of t to the first power will always be equal to its coefficient, which in this case is 5. And then finally, the derivative of 7, that's going to be 0, because 7 is a constant, and the derivative of all constants is 0. Okay, so now we have dx dt and dy dt. Now let's find our first derivative, dy dx. And so dy dx will be equal to dy dt divided by dx dt. So we'll have 2t plus 5 divided by 3t squared. So let's write that down. 2t plus 5 divided by 3t squared. Okay, now there's nothing for us to simplify here. This is in its simplest form. And so this is dy dx, the first derivative of our parametric equations. Now what we want to do is use this first derivative to calculate our second derivative, because the second derivative involves taking the derivative with respect to t of that first derivative. And so our second derivative will look like this. It will be equal to the derivative with respect to t of that first derivative, 2t plus 5 divided by 3t squared. And then we will divide that by the same denominator from our first derivative, which is dx dt. All right, and dx dt is equal to 3t squared, so we'll have 3t squared in the denominator for our second derivative. All right, so we've set up our second derivative, but we still need to find it because we need to differentiate this first derivative with respect to t. And notice that we have a rational expression here, right? We have a fraction, and both the numerator and denominator involve that variable t. And so what we have here is a quotient of two functions. So to find the derivative, we will need to use the quotient rule. And so if you don't remember the quotient rule for derivatives, I'll have it up here on the screen for you to reference. But here's how it's going to work. We start by taking the denominator, or the bottom function, and multiplying it by the derivative of the numerator, or the top function. So we're going to have 3t squared times the derivative of 2t plus 5. Now the derivative of 2t, that's just going to be 2. The derivative of t to the first power will be equal to the coefficient. And then the derivative of 5 is 0 because 5 is a constant, and the derivative of all constants is 0. So the derivative of that top function is just 2. And then next we're going to subtract the top function, or the numerator, and multiply it by the derivative of the denominator, or the bottom function. So we'll have 2t plus 5, and we want to multiply that by the derivative of the denominator, which if we use the power rule for derivatives, we'll multiply this 2 down, 2 times 3 is 6, and subtract 1 from the exponent, so we'll have a power of 1, so the derivative will be 6 times t to the first power. Alright, and this will all be divided by the denominator squared. So we're going to have 3t squared squared. So we'll have 3t squared squared. Okay? And then this is all still divided by this 3t squared, which is in the denominator of our second derivative. So we'll have 3t squared. Okay, and so this would be our second derivative, but it's pretty messy. We need to simplify it a little bit before we can use it to determine the concavity at t equals 2. I guess if you wanted to, you could plug 2 right into this form and find the value of your second derivative, but that would be pretty messy. So let's simplify this. First of all, notice that dividing by 3t squared would be the same as just multiplying that into the denominator of this numerator, right? We could view this expression as a fraction divided by another fraction, right? 3t squared divided by 1 would be the fraction in the denominator. And when you're dividing by a fraction, that is the same as multiplying by the reciprocal of that fraction, right? So if we flip the numerator and denominator, we can multiply this top fraction by that reciprocal. So we'd be multiplying by 1 divided by 3t squared. So what we'll really have is that we're just multiplying 1 through this numerator and 3t squared into this denominator. All right, so if I clean up my work here, instead of dividing by 3t squared divided by 1, we can just multiply by 1 divided by 3t squared. Okay, and then we can remove these parentheses here, and then just multiply 1 by the numerator, which won't change anything, and then multiply 3t squared into the denominator. And that will make this 3t squared squared become 3t squared cubed, right? We have another 3t squared that we're multiplying in, so we'll have 3t squared cubed. Okay, so that will be the denominator of our second derivative. We're going to have 3t squared cubed. And then for the numerator, we need to simplify it a little bit. So let's multiply 2 by 3t squared. That will be 6t squared. And then we're going to subtract this quantity times 6t. So let's distribute 6t into this quantity. Let's multiply it by both of these terms. 6t times 2t is 12t squared. So we'll have 12t squared. And then 6t times 5 will be 30t. So we'll have plus 30t. Okay? Now let's distribute this negative through this quantity. And this will be equal to 6t squared minus 12t squared minus 30t. And then that's still divided by 3t squared cubed. And now we can add our like terms of 6t squared and negative 12t squared. And so if we combine those, that will be negative 6t squared. And so if I clean up my work again, our second derivative will be equal to negative 6t squared minus 30t divided by 3t squared cubed. Okay, and so now our second derivative is much simpler. We can now work with it to determine the concavity at this value of t for our parametric equations. So what we want to do is determine the concavity at t equals 2. So what we can do is plug that value of t into this second derivative. So if we do that, we'll have the second derivative evaluated at t equals 2, and that will be equal to negative 6 times 2 squared minus 30 times 2 divided by 3 times 2 squared cubed. Okay, so I just replaced each of these t's in our second derivative with 2 because t is equal to 2. All right, now 2 squared is 4, and 4 times negative 6 is negative 24. So this is equal to negative 24, and then we will subtract 30 times 2, which is 60. So we'll have 60, and then we'll divide by 3 times 2 squared. 2 squared is 4, so 4 times 3 is 12. So we have 12 cubed in the denominator. All right, and then negative 24 minus 60, that will be negative 84. And so if I clean up my work a little bit, this will be equal to negative 84 divided by 12 cubed, and 12 cubed is 1,728. And then if you want to simplify this, you don't have to because we're just looking for the sign of the second derivative. But if you wanted to simplify this further, both 84 and 1,728 are divisible by 12. So if we divide both of them by 12, this would be equal to negative 7 divided by 144. All right, and so now we have evaluated our second derivative at t equals 2, and we have a negative value for that second derivative. Negative 7 divided by 144 is a negative value, and so it's less than 0, which means that at that value of t equals 2, the curve represented by these parametric equations is going to be concave down. All right, so at t equals 2, the curve is concave down because the second derivative at that value of t is negative. If it was positive, then the curve would be concave up, but since it's negative, it's concave down. All right, and so that is the final answer to this example. Okay, so here's our next example. We want to determine the t intervals on which the curve represented by the parametric equations is concave downward or concave upward. And we have x equals the square root of t and y equals the natural log of t. All right, so this example is slightly different than what we did in the previous example. We're still working with concavity, which means we're still going to need to find the second derivative for these parametric equations, but this time rather than determining the concavity at one particular value of t, we want to find the intervals of t values for which our curve is concave up or concave down. And that's a slightly different process, but I'll talk about how we determine those intervals once we find our second derivative. That's going to be our first focus here. All right, and before we do that, just note that for these parametric equations, that we have the square root of t and the natural log of t, the square root of t is not going to be defined for negative values of t, right? You can't take the square root of a negative value and get a real result. You would get an imaginary number, which we don't want to work with. And the natural log function is not defined for values less than or equal to 0, right? The natural log of 0 is undefined, and the natural log function is also not defined for any negative values. And so what we can make a note of here is that t will only be defined for values greater than 0. In other words, positive values of t. All right, so these two parametric equations are only defined for t values greater than 0. Okay, so keeping that in mind, let's find our second derivative, and in order to find that, we first need our first derivative, dy dx. Let's find that by taking the derivative of x and y with respect to t. And so let's start with dx dt, the derivative of x with respect to t. Remember that the square root of t could be rewritten to be t to the 1/2 power, right? Taking the square root of a value and raising that value to the 1/2 power is the same thing. And so now we can see how to use the power rule for derivatives here. We can multiply that exponent down and subtract 1 from the exponent. And so dx dt will be equal to 1/2 times t to the power of negative 1/2. We multiply 1/2 down, and 1/2 minus 1 is negative 1/2. All right, so that's dx dt. And then dy dt, that will be equal to the derivative of the natural log of t. And the derivative of the natural log of t is just going to be 1 divided by t. Right? The derivative of a natural log function is always going to be 1 divided by whatever function is inside the natural log function, and then you would multiply by the derivative of that inside function. And in this case, the derivative of t is just 1, so we have 1 divided by t times 1, which is just 1 divided by t. Okay, so that's dy dt, and we also have dx dt, so now we can find our first derivative, dy dx, that will be equal to dy dt divided by dx dt. So we'll have 1 divided by t divided by 1/2 times t to the power of negative 1/2. Okay, now let's simplify this a little bit because we're going to need to take the derivative of this again to find our second derivative. So what we can do is move this 1 divided by t out to the front. So our first derivative will be equal to 1 divided by t times 1 divided by 1/2 times t to the power of negative 1/2. And we can combine t and t to the power of negative 1/2. Right? If we multiply them together, we will add their exponents. We'll have this power of 1 plus this power of negative 1/2. That will give us t to the power of positive 1/2. And so this is equal to 1 divided by 1/2 times t to the power of positive 1/2. But dividing by 1/2 is the same as multiplying by 2. So instead of dividing by 1/2, I'm just going to erase that and multiply that 2 into the numerator and have 2 divided by t to the 1/2 power. All right, and then because we're going to need to take the derivative of this again for our second derivative, I'm going to move t to the power of negative 1/2 to the numerator and make that exponent negative. That will make it easier for us to differentiate using the power rule for derivatives. So our first derivative is equal to 2 times t to the power of negative 1/2. So now we have our first derivative, dy dx is 2 times t to the power of negative 1/2. Now let's use that to find our second derivative. Our second derivative will be equal to the derivative with respect to t of our first derivative, 2 times t to the power of negative 1/2, and then we are still going to divide that by dx dt, which is this expression right here. We have 1/2 times t to the power of negative 1/2. Okay, now let's take the derivative of our first derivative with respect to t. We'll multiply this exponent down. 2 times negative 1/2 will be negative 1, and then we'll subtract 1 from that exponent, and so this will be equal to negative t to the power of negative 3/2. Right, negative 1/2 minus 1 is negative 3/2. And this is going to be divided by 1/2 times t to the power of negative 1/2. All right, now to simplify our second derivative, we can move t to the power of negative 3/2 to the denominator by making that exponent positive. So this will be equal to negative 1 divided by 1/2 times t to the power of negative 1/2 times t to the power of positive 3/2. All right, now if we simplify this further, remember that dividing by 1/2 is the same as multiplying by 2. So this would be equal to negative 2 divided by t to the power of negative 1/2 times t to the power of 3/2. We can combine them by adding their exponents. So negative 1/2 plus positive 3/2 will be positive 2/2. So we'll have t to the power of 2 divided by 2, right? That's 2/2, but 2 divided by 2 is just 1. So really, what we have is negative 2 divided by t to the first power. And so right here, we have our second derivative for this set of parametric equations. Now what we can do using this second derivative is determine our t intervals for which the curve represented by these equations is concave down or concave up. And so for this example, we could do this pretty intuitively because our second derivative is fairly simple. We just have negative 2 divided by t. We know that when the second derivative is positive, that the curve will be concave up, and when the second derivative is negative, the curve will be concave down. And we also know that t is only defined for values greater than 0, right? We determined that at the beginning because of our parametric equations. The natural log of t is only defined for t greater than 0. And so that means we can only plug positive values of t into this second derivative. And if we can only plug positive values of t into the second derivative, then we're always going to have negative 2 divided by some positive value. And a negative value divided by a positive value will always be negative, and so our second derivative will be negative for all values of t. And so what we learn here is that when t is greater than 0, our curve will be concave down, right? Because for all values of t, the second derivative will be negative, and when the second derivative is negative, our curve is concave down. And another way that we could write this is to say that our curve is concave down for the interval of t from 0 to positive infinity. All right, so either one of these answers is correct. These both represent the t interval of concavity for the curve represented by these parametric equations. All right, and so like I said earlier, this was pretty intuitive because this second derivative is fairly simple, but that's not always going to be the case. For many second derivatives of parametric equations, they will be much more complicated, and so it won't be as simple to determine the intervals of concavity for the values of t. And so the more general process that we can use to determine the intervals of concavity is to determine what values of t might have the potential to be a value where the concavity will change for a curve. Because remember, what concavity represents is the change in the slope for a function. And so when the second derivative is positive, the slope is increasing, and when the second derivative is negative, the slope is decreasing. And so the only way that the slope will change from being increasing to decreasing, or vice versa, is if at some point it becomes constant, or the second derivative is 0, or if the rate of change of the slope is undefined, meaning that the second derivative is an undefined value. And the only way that those two things occur is if the numerator is equal to 0, because 0 divided by anything will be 0, so the second derivative would be 0, or if the denominator is 0, meaning that we would be dividing by 0, so the second derivative would be undefined. So what we can do to find potential points where the concavity might change is set the numerator and denominator of our second derivative equal to 0, solve for any values of t, and then use those values of t to help us determine our intervals of concavity. Right, so in this case, there's nothing that would make the numerator of this second derivative equal to 0. Negative 2 is always going to be negative 2. There's no value of t in this numerator that will change that value. But in the denominator, we have t. If we set that denominator equal to 0, that tells us when t equals 0, that our curve has the potential to change concavity. But we also know in this case that t is only defined for values of t greater than 0. And so if we were to draw a number line for our t values for this curve, we would start at 0 and go to infinity. The interval from 0 to infinity would represent the only interval where the curve could be concave up or concave down. And so all we have to do to determine if it's concave up or concave down at this point is just plug in a value of t between 0 and infinity and see if the second derivative is positive or negative. So let's say we chose t equals 1. If you plug 1 into the second derivative, you'll have negative 2 divided by 1, which is equal to negative 2. And so the second derivative is negative, which means it's less than 0, which means that our curve is concave down for this interval from 0 to infinity. So you could represent that with a negative sign. The second derivative is negative, and so that leads us to our same answer that we got earlier, that our curve is concave down for the interval from 0 to infinity. Okay, and so that is the final answer to this example. We didn't have to use that second method of drawing the number line and testing a value of t for this example because our second derivative was pretty simple, but that second method that we just went through will be very helpful for other examples where the second derivative is not as nice. All right, and so let's take a look at another example of determining the t intervals of concavity for a curve represented by parametric equations. All right, so here's our next example. We want to determine the t intervals on which the curve represented by the parametric equations is concave downward or concave upward. And this time we have x equals sine t and y equals cosine t, and we're only looking at the values of t from 0 to pi for these parametric equations. All right, so once again, we want to find intervals of concavity, and so since we're working with concavity, we know we need to find the second derivative for our set of parametric equations. And so let's work on that first. And so we need to begin by finding the first derivative because we need that first derivative to find the second. And so let's take the derivative of both of our parametric equations with respect to t. dx dt will be equal to the derivative of sine t, and the derivative of sine is cosine, so we'll have cosine t as our derivative. And then dy dt, the derivative of y with respect to t, will be the derivative of cosine t, and the derivative of cosine is negative sine, so we'll have negative sine t. All right, and so now that we have dy dt and dx dt, we can find dy dx, our first derivative, and dy dx will be equal to dy dt divided by dx dt. So we'll have negative sine t divided by cosine t. Okay, now you can leave your derivative in this form if you wanted to, but if you can simplify your first derivative, you should, because you're going to need to take the derivative of this again for your second derivative, and so you want this to be as simple as possible. And notice that we have sine divided by cosine. If you're familiar with your trigonometric identities, you know that sine divided by cosine is equal to tangent, and so our first derivative is really equal to negative tangent t. Okay, so we still keep that negative, that doesn't go away, but sine divided by cosine is tangent. All right, so our first derivative is negative tangent t. Now let's use that to find our second derivative. The second derivative will look like this. It will be equal to the derivative with respect to t of that first derivative of negative tangent t. And then we're going to divide by dx dt, and dx dt is equal to cosine t, so we'll have a denominator of cosine t. All right, now if we take the derivative with respect to t of negative tangent t, remember that the derivative of tangent is secant squared, so this will be equal to negative secant squared t divided by cosine t. And so this would be our second derivative, but we can simplify this further. Note that secant is equal to 1 divided by cosine, right? If you remember your trigonometric identities, cosine t is equal to 1 divided by secant t, which means that secant t is equal to 1 divided by cosine t. All right, so we can rewrite secant squared t to be 1 divided by cosine squared t. And so this will be equal to negative 1 divided by cosine t times cosine squared t. And cosine t times cosine squared t will be cosine cubed t. So this is equal to negative 1 divided by cosine cubed t. Okay, and so now we have our second derivative. Now what we want to do is use that second derivative to determine the t intervals of concavity for the curve represented by these parametric equations. Now what we want to do in this case, since our second derivative is a little bit more complicated, it's not as clear as the last example what values of t will make this second derivative positive or negative. All right, so what we want to do is that other method. Let's find any values of t that might be values where the curve might change concavity, and we find those values of t by setting the numerator and the denominator equal to t and solving for t. Now in this case, the numerator is -1. There's no t's in that numerator, so there's no need to set the numerator equal to 0. The numerator will just never be 0 in general. And so let's look at the denominator. Let's set cosine cubed t equal to 0. And so that would be the same as cosine t cubed is equal to 0. And so if we take the cubed root of both sides, that will give us that cosine t is equal to 0. And now what we have to do to solve for t is determine what values of t for cosine give us 0 for this interval of t values, right? So on this interval from 0 to pi, the only value of t that will make cosine equal to 0 is pi divided by 2. All right, cosine of pi divided by 2 is 0, and there are some other values that make cosine equal to 0, but none of them are on this interval from 0 to pi. Another example would be 3 pi divided by 2. Cosine of 3 pi divided by 2 is 0, but 3 pi divided by 2 is greater than pi, so it's not on this interval. All right, so t equals pi divided by 2 is the only solution to this equation on this interval. And so what we find here is that at this value of t, our curve has the potential to switch concavity. It might be concave up until that value of t, and then it might switch to concave down, or vice versa. So what I recommend that you do here is draw a number line for your values of t. In this case, our values of t range from 0 to pi, and then you also want to add that value of t where the concavity might change. And so that's halfway in between here at pi divided by 2. All right, and so what you can see on this number line is that there's going to be two intervals of t values where the concavity might be different. And those two intervals are from 0 to pi divided by 2 and from pi divided by 2 to pi. Okay, remember, our t values do not include 0 and pi. They're between 0 and pi, so that's why we have open brackets for 0 and pi. And so this interval right here from 0 to pi divided by 2 represents this part of our number line, and then this part of the number line is represented by this interval from pi divided by 2 to pi. And so now what we can do is determine whether these t intervals tell us that our curve is concave up or down by choosing a value of t between the endpoints for each interval and plugging them into the second derivative to see if it gives us a positive value or a negative value. So let's start with our first interval from 0 to pi divided by 2. I'm going to choose the t value of pi divided by 4. That is in between 0 and pi divided by 2. We can plug that into our second derivative to see if it's positive or negative. Now, just a quick note, you can pick any value of t that you like that is between these two values. I chose to use pi divided by 4, but certainly you could use pi divided by 3 or pi divided by 6 or any other value of t between those two values. This is just the one that I chose to use. And so when t equals pi divided by 4, let's plug that into our second derivative. We'll have -1 divided by cosine cubed of pi divided by 4. Now cosine of pi divided by 4, that's equal to the square root of 2 divided by 2. And so if we have cosine cubed of pi divided by 4, we just have to cube both sides. And so the square root of 2 cubed will be the square root of 2 times itself 3 times. So the square root of 2 times itself is 2, and then times another square root of 2 will give you 2 square roots of 2, and that will be divided by 2 cubed. So you'll have 8 in the denominator, and 2 divided by 8 leaves you with 1/4. And so really, this will be the square root of 2 divided by 4. And so that is going to be the value of cosine cubed of pi divided by 4. So if I erase this work, let's write that in here. This is going to be equal to -1 divided by the square root of 2 divided by 4. But when you divide by a fraction, that's the same as multiplying by the reciprocal. And so really this is equal to -1 times 4 divided by the square root of 2. So we'll have -4 divided by the square root of 2. Okay, now I'm not worried about rationalizing this or anything. It's okay to have the square root of 2 in the denominator here. All we're worried about is the sign of this value for our second derivative. When t equals pi divided by 4, our second derivative is equal to this value, which is negative, which means it's less than 0, which means that our curve is concave down for this interval from 0 to pi divided by 2. So I'll label that on our number line here with a negative sign. For this interval, our curve will be concave down, but now let's determine what is going to happen for this other interval from pi divided by 2 to pi. In this case, I'll choose my value of t to be 3 pi divided by 4. That is in between pi divided by 2 and pi. And so if we plug 3 pi divided by 4 into the second derivative, we will have negative 1 divided by cosine cubed of 3 pi divided by 4. Now cosine of 3 pi divided by 4 will be the negative square root of 2 divided by 2. And so we're going to be cubing that as well. And so instead of having the positive square root of 2 divided by 4, we're going to have the negative square root of 2 divided by 4. All right, we're going to get that same value, but the sign will be different, because cosine of 3 pi divided by 4 is the negative square root of 2 divided by 2, and cubing a negative value will still result in a negative value. And so this will be equal to negative 1 divided by the negative square root of 2 divided by 4, and those two negatives will cancel out, and this will be equal to positive 4 divided by the square root of 2. And that is a positive value for our second derivative. It is greater than 0, which means that for this interval, our curve is concave up. So if I label that on our number line here with a plus sign, now we have determined that for this interval, our curve is concave down, and for this interval, our curve is concave up. And so if I clean up my work here, let's finalize our answer. For the curve represented by these parametric equations, the interval where the curve is concave up will be from pi divided by 2 to pi, and the interval where the curve is concave down will be from 0 to pi divided by 2. That is the final answer to this example. Let's take a look at one more example for this video. All right, so here's our last example. Once again, we want to determine the t intervals on which the curve represented by the parametric equations is concave downward or concave upward. And so once again, in order to determine those intervals of concavity, we need to find the second derivative for our set of parametric equations. In this case, we have x equals t squared plus 9 and y equals t cubed minus 6t squared plus 2t. And so let's get right into this. Let's start by finding the first derivative of our parametric equations so that we can find our second derivative. And so let's take the derivative of x with respect to t. dx dt will be equal to the derivative of t squared plus 9. Using the power rule for derivatives, the derivative of t squared will be 2t. And then the derivative of 9 is a constant, so the derivative will be 0. So we just have 2t for dx dt. Then for dy dt, that will be equal to the derivative of t cubed minus 6t squared plus 2t. We can use the power rule for derivatives on our terms here. If we multiply this exponent down and subtract 1 from the exponent, we'll have 3t squared. And then we will have 2 times the negative 6, that's a negative 12, and then t to the first power. And then the derivative of 2t, that's just going to be 2, because t to the first power, the derivative, will just be equal to the coefficient. And so dy dt is equal to 3t squared minus 12t plus 2. Okay, and so now that we have dx dt and dy dt, we can find our first derivative, dy dx. That will be equal to dy dt divided by dx dt. So we'll have 3t squared minus 12t plus 2 divided by 2t. All right, and so this is our first derivative, dy dx, and we can use this to find our second derivative. But before we do that, we can simplify this a little bit to make it easier to differentiate it with respect to t in order to find that second derivative, because currently we would need to use the quotient rule to take the derivative of this because we have a fraction or an expression with t divided by another expression with t. But what we can do is divide each of these terms by 2t, and what that would give us is that our first derivative is equal to 3t squared divided by 2t minus 12t divided by 2t plus 2 divided by 2t. And this is going to simplify pretty nicely into an expression that is a whole lot easier to differentiate with respect to t. Note that we have t squared divided by t. One of those t's will cancel out with one of those, so we're just going to be left with 3 halves times t to the first power. Then we have negative 12 divided by 2. That will be negative 6, and t divided by t will just be 1. Those t's will cancel out, so we're just left with negative 6. And then for this last term, 2 divided by 2 is 1, so those 2's will cancel out, and we're just left with 1 divided by t, but we could rewrite that by moving t to the numerator. which would make its exponent negative, and so we would have t to the power of -1. And now we have a much easier expression for our first derivative that we can use to find the second derivative. So now let's work on finding our second derivative. The second derivative will be equal to the derivative with respect to t of our first derivative, which is 3/2 times t minus 6 plus t to the power of -1, and that will be divided by dx dt, which is 2t. So we'll have 2t. Okay, and so now let's differentiate our first derivative with respect to t. The derivative of 3/2 times t will just be 3/2, the coefficient of t to the first power. So we'll have 3/2, and then the derivative of -6, that will be 0 because -6 is a constant and the derivative of all constants is 0. So we don't need to worry about that. And then we have t to the power of -1. We'll multiply that -1 down and then subtract 1 from the exponent. So we'll have minus t to the power of -2, right? Multiplying -1 down makes it negative. So we have -t, and then -1 minus 1 is -2. And then this is still divided by 2t. All right, now we can rewrite t to the power of -2 by moving that expression to the denominator of this term. We can't move it to the denominator of this entire fraction because we're subtracting it from another value. If instead we had 3/2 times t to the power of -2, we could then move it to this denominator down here. But because we're subtracting it from a term, we can only move it to the denominator of its own term. And here's what I mean by that. This would be equal to 3/2 minus 1 divided by t squared divided by 2t. All right, so we kept it in that position, but we just made it 1 divided by t to the positive power of 2 instead of -2. All right, and so now what we can do to simplify this further, I don't like having two fractions in the numerator here. What I'm going to do is multiply by a form of 1 of t squared divided by itself. What that will do is cancel out with this fraction and make it just 1, which will be a whole lot easier to work with. And we can do this because multiplying by a form of 1 doesn't change the value of this expression, right? You can always multiply by 1. And so our second derivative will be equal to 3/2 times t squared minus 1 divided by 2t cubed. All right, t squared times 3/2 is 3/2 times t squared. T squared times 1 divided by t squared will just be 1 because we have t squared divided by itself, and that is just going to be 1. And then t squared times 2t will be 2t cubed. Okay, and so now we have a second derivative that we can work with to determine the t intervals of concavity for the curve represented by these parametric equations. And now for this second derivative, it's pretty complex. It's not going to be very simple to intuitively decide what values of t will make it positive or negative so that we can find our intervals of concavity. So instead, we're going to need to use that method of finding values of t where the concavity might change. And we find those values of t by setting the numerator and denominator equal to 0 separately and then solving for t. So let's start with the numerator. Let's set 3/2 t squared minus 1 equal to 0 and solve for t. We'll start by adding 1 to both sides of the equation, and we'll have 3/2 times t squared is equal to 1. And then to isolate t squared, we can divide both sides by 3/2, which would be the same as multiplying by the reciprocal of 3/2, which would be multiplying by 2/3. So we'll have t squared is equal to 2/3. And then to solve for t, we need to take the square root of both sides of the equation. So we'll have t is equal to plus or minus the square root of 2/3. All right, taking the square root of a value could result in a positive value or a negative value, so we need to account for both of those values of t for this curve. All right, so at t equals positive square root of 2 divided by 3, or t equals the negative square root of 2 divided by 3, the curve represented by these parametric equations could change from being concave up to concave down, or vice versa. So those are the values of t that we found from the numerator. Now let's set the denominator equal to 0. So we'll have 2t cubed is equal to 0. And now let's solve for t. Dividing both sides by 2 will give us t cubed is equal to 0. And then taking the cubed root of both sides of the equation will give us that t is equal to 0. All right, so now we have one more value of t where our curve could change concavity. We have these two values of t and then t equals 0. All right, so now what we can do is draw a number line of our t values. This is going to help us determine our intervals of concavity. We know that these two parametric equations are defined for all values of t, So this side of our number line will represent values of t towards negative infinity, and this side of our number line will represent values of t towards positive infinity. And then we want to mark all of our values of t that we found from setting the numerator and denominator of the second derivative equal to 0. So we'll have t equals 0, and then t equals the negative square root of 2 divided by 3, and t equals the positive square root of 2 divided by 3. Okay, so we have 4 different intervals where our curve could be concave up or concave down. And so let's write them down. We have negative infinity to the negative square root of 2 divided by 3. We have the negative square root of 2 divided by 3 to 0. Then we have 0 to the positive square root of 2 divided by 3, and the positive square root of 2 divided by 3 to infinity. All right, so we have these 4 different intervals that we need to check to see if our curve is concave up or concave down for. And so let's start with this first interval. What we want to do is choose a value of t between those 2 endpoints to plug into our second derivative to see if it is positive or negative. And the square root of 2 divided by 3, I'm going to make a note of this up here, that is approximately equal to 0.82. So the negative square root of 2 divided by 3 would be negative 0.82. And so a value between negative 0.82 and negative infinity could be a lot of different values. I'm going to choose a negative 1. That would be in between those 2 endpoints. So when t equals negative 1, we'll plug negative 1 into our second derivative. So we'll have 3 halves times negative 1 squared. Negative 1 squared is positive 1. So we'll have 3 halves times 1 minus 1 divided by 2 times negative 1 cubed. And negative 1 cubed is negative 1. And so we have 2 times the negative 1. So this is equal to 1 half, right? 3 halves minus 1 is 1 half, divided by 2 times the negative 1, which is negative 2. And 1 half divided by negative 2 will be negative 1/4. All right, and negative 1/4 is less than 0. That is a negative value for our second derivative, which means that for this interval, our curve is concave down. So I'll mark that with a negative sign. Okay, so that takes care of this interval. Our curve is concave down. Now let's work on our next interval. This time we have the negative square root of 2 divided by 3 to 0. And so to choose a value of t between those 2 values, once again we know that the negative square root of 2/3 is negative 0.82. So I'm going to choose negative 1 half. That would be negative 0.5. So when t is equal to negative 1 half, let's plug that into our second derivative. We will have 3 halves times negative 1 half squared minus 1 divided by 2 times negative 1 half cubed. Negative 1 half squared will be positive 1/4. So this is equal to 3 halves times 1/4 minus 1 divided by 2 times negative 1 half cubed. That is going to be negative 1/8. All right, when you cube a negative value, it's still negative, and 2 cubed is 8. So negative 1 half cubed is negative 1/8. Now if we simplify, 3 halves times 1/4 will be 3/8 if we multiply the numerators and denominators. So this is equal to 3/8 minus 1 divided by 2 times negative 1/8, which will be negative 1/4. So we have negative 1/4. All right, now 3/8 minus 1, that will be negative 5/8. So I'm going to erase this, and we'll have negative 5/8. And then a fraction divided by another fraction, we can determine what that is equal to by multiplying the numerator by the reciprocal of the denominator. So this will be equal to negative 5/8 times the reciprocal of negative 1/4, which will be negative 4 divided by 1. And so these 2 negatives will cancel out, so this result will be positive. 5 times 4 is 20, and so this is equal to positive 20/8. And both of these values are divisible by 4. 20 divided by 4 is 5, and 8 divided by 4 is 2. And so this is equal to positive 5 halves. All right, so when t equals negative 1 half, our second derivative is equal to positive 5 halves. And so since that is positive, it's greater than 0, that means that our curve is concave up on this interval. So I'll label that on our number line with a plus sign. We're concave up. Now let's look at our next interval. We have 0 to the square root of 2 divided by 3. The square root of 2 divided by 3 is positive 0.82. So in this case, I'm going to choose t equals positive 1 half. That is going to be in between those 2 endpoints. And so when t equals positive 1 half, if we plug that into our second derivative, we're actually going to get a very similar result that we got for t equals negative 1 half. the sign is just going to be different. So I'm going to go through this pretty quickly. When t equals positive 1/2, we'll have 1/2 squared, which is 1/4, times 3 halves. So we'll have 3/8 minus 1 divided by 2 times 1/2 cubed. And 1/2 cubed is 1/8. And 1/8 times 2 is 1/4. So we have 1/4. And then 3/8 minus 1 is negative 5/8. So this is equal to negative 5/8 divided by 1/4. And dividing by a fraction is the same as multiplying by its reciprocal. So this is equal to negative 5/8 times 4 divided by 1, which is the same exact multiplication we had for our previous calculation, except now it's negative. So this is equal to negative 28, which will be equal to negative 5/2. And negative 5/2 is less than 0, it's negative, and so for this interval, our curve will be concave down. So let's make a note of that on the number line. Okay, and so now we only have one more interval left to check, so let's do that next. Lastly, we have the square root of 2 divided by 3 to infinity. So let's pick a value of t between those two values. Remember that the square root of 2 divided by 3 is 0.82. So in this case, I'm going to choose t equals positive 1 because that will be bigger than that value and less than infinity. And so when t equals 1, we'll have 3 halves times 1 squared. That will be 1 times 3 halves. So we will have 3 halves minus 1 divided by 2 times 1 cubed. 1 cubed is 1, so 1 times 2 is 2. So we have 2 in the denominator. And 3 halves minus 1 is 1/2. So this is equal to 1/2 divided by 2, which will be equal to 1/4. And 1/4 is positive. It's greater than 0, which means that for this interval, our curve will be concave up. The second derivative is positive. All right, and so now we have determined the concavity for each of these intervals on our number line. Now all we have to do is finalize our answer. All right, so for the curve represented by these parametric equations, the curve is concave down for the values of t from negative infinity to the negative square root of 2 divided by 3. That's this interval right here, but it's also concave down for this interval, so we will union that with 0 to the positive square root of 2 divided by 3. All right, so those are the values of t for which our curve is concave down, and then it's concave up for the interval from the negative square root of 2 divided by 3 to 0. That is this interval right here, and then we want to union that with this interval where it is also concave up. So we'll union that with the square root of 2 divided by 3 to infinity. And so right here, we have our t intervals of concavity for the curve represented by these parametric equations. Okay, and so with that, this is the last example for this video. So if you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.